So yeah, just a quick intro. Charles and Rachel would be delivering a tutorial on Pangeo Forge, an ETL platform for cloud optimized analysis ready for data.
Great. I'm going to begin by giving a few overview slides, and then we'll get into the tutorial portion.
I'm going to explain quick what will happen while Charles is logging off and logging back on. So Charles will spend about 20 minutes. We're going to talk about Pangeo Forge, which he'll explain in more detail as a tool for kind of creating cloud optimized data sets. And then I'll take about 20-ish minutes and go through a tutorial on using Pangeo Forge. So we'll take some data that's OISST sea surface temperature and we'll convert it to Zarr. In the last 2 minutes, we'll then talk about kind of two pieces. There's the Pangeo Forge recipes and Pangeo Forge cloud. So then we'll talk about the cloud piece and how you can run that processing on the cloud. And hopefully have some time for questions. We'll see how things shake out here. We will be using or kind of doing with this for folks who are earlier on for the Zarr tutorial, some of the same compute the binder resources. So we'll have to kind of see how we go there as we get to that point, folks starting that, or if they want to install things locally. So we'll hit that bump when we get there.
Do we want to share the binder link now, just so people can start spinning things up and getting those errors out of the way while Charles is doing the introduction?
Yeah, it sounds great. So I'll share two of them in the chat, Dan. I'll share Pangeo Forge to binder. I'll share the my binder, and then I'll also give a couple instructions. If folks want to install locally, they can do that as well. So folks can go ahead. There's 3 different ways you posted to either start a binder link or install locally. And so you're welcome to kind of, in theory, we're all sort of spread evenly between those two or between those different options. So folks can start clicking the link. And if you haven't done one of these tutorials with a binder link before, what'll happen is a page will pop up in your browser and it will start building an environment. And you can, it'll take a few minutes for that to start up while it builds the environment, and eventually should launch like a workspace with a Python notebook in it. If it isn't working, there's a lot of, typically it's sort of refresh is kind of the thing to go to, but if it can also post in the Gitter and we can do our best to help.
Great. So I think you can see my Gitter. So let's make it show the right thing and make up for some lost time. Okay, hi everybody. My name is Charles Stern, and I'll introduce my co-presenters momentarily. We're going to be speaking about Pangeo Forge, which is a cloud-native data library and a data ingestion transformation tool for ocean weather and climate science. So I'm here today with Rachel Wegener from the University of Maryland, and also you've heard Ryan Abernathy earlier in the session, and he's also here to support the project. He's the creator of the project. So you've already heard a lot, so I just have one slide about this right now, that analysis-ready cloud optimized data is very fast. You've already heard about tools like Xarray and even the Zarr format, and the incredibly high throughputs that can be achieved when using these tools together on the cloud. Here's a reference if you're interested. It may have been mentioned in some of the other presentations discussing some of those performance characteristics. But what we want to discuss today is the problem of how to make analysis-ready cloud optimized data, and particularly how difficult that is. There's a lot of interlocking, very difficult skills, hard to achieve skills required to create analysis-ready cloud optimized data. There's the domain expertise of the scientific domain to which the data relates itself. There's technological knowledge about how to efficiently produce cloud optimized formats. There are compute infrastructure concerns related to producing cloud optimized data, and obviously there's also this slide may have been clipped a little bit, but there's also the communication aspect of creating a platform to disseminate and distribute the data that's been communicated in a clear way. So this is a very difficult challenge. Pangeo Forge, I see we're getting a little clipped here. Pangeo Forge aims to provide a platform that allows more people to participate in this data curation process. And let's talk about our inspiration for that. Our inspiration for Pangeo Forge is the platform Conda Forge, which many may be familiar with. Conda Forge is a community repository and community curated repository of precompiled software binaries for a lot of very well-loved and well-used packages in the scientific Python ecosystem. This is too small to perhaps see in the slide, but Conda Forge now hosts well over 14,000, perhaps over 15,000 community contributed recipes for building these binaries. And we think it's a very successful model of crowdsourcing this type of resource for the community. So Pangeo Forge has two main components. It has a Pangeo Forge recipes, which is a Python package for building up pipelines for data transformation from archival formats into cloud optimized formats. And we also have Pangeo Forge Cloud, which is our cloud platform for executing those recipes. The recipes themselves, as we'll see today, can be executed on their own, on your own local infrastructure. But by using Pangeo Forge Cloud, we have the advantage of taking advantage of a much larger cloud compute infrastructure, as well as contributing to a community catalog. So just briefly about the recipes, see if a slightly larger zoom will be useful to us here. Just briefly about the recipes. Recipes are Python objects, and Rachel will talk to you about those momentarily, which have sensible defaults and are really quite easy to compose if you're familiar with some basic Python concepts. The cloud, again, just to recap, is composed of a few different modular components and is the infrastructure and execution environment for those recipes to execute them at scale. So a feedstock, just to cover a few key vocab words, is a concept borrowed from Conda Forge, and a feedstock is a GitHub repository where these Python recipes live. The bakery is a cloud compute cluster that actually executes those recipes, and a storage location could be on storage providers such as Amazon S3 or Google Cloud Storage, is where the bakery, which has executed the recipe living in the feedstock, deposits that output data. So our vision is really to have a collaborative data curation process that by hosting these feedstocks, which are GitHub repositories on GitHub, we provide a place for all of these nice data users, data managers, data producers to have a conversation around the quality of that data over time. Once the data has been created, the recipe that was used to create it lives in one of these feedstock repositories. And as you can see on this slide, all of these folks are participating in a conversation around improving the quality of that data. So this really gets at one of our core values, which I'll just mention as we wrap up these slides, that we're trying to help the community realize through Pangeo Forge, which is transparency and reproducibility of the data pipelines, which is something that we see as missing from alternative ways of methods of ARCO data production today. And just building on that theme, Pangeo Forge is a 100% open project. We're just showing some screenshots here of some of the repositories and project boards that are involved in producing this platform. So we certainly welcome everyone to take a look and even participate, and hope you will participate in the project at github.com/Pangeo-Forge. So this gets into our tutorial section, and I'll conclude the screen share of these slides just by saying that, all of us today are guinea pigs. This is a brand new platform, and we're really grateful for your interest in it. And with your feedback, we hope to make it a much, very robust and useful tool for all of us to use, to produce ARCO data in the months and years to come. And so with that, I will stop my screen share and hand it over to Rachel to begin the tutorial portion.
Okay, are we all looking at the tutorial here on my screen?
Yep.
Lovely. Okay, so what we'll go through in the next bit of time is the tutorial. This is the tutorial that is on the Pangeo Forge documentation. So if we don't get to the end, or if you get lost or you're unsure kind of what the next step is, all the information about the share is in the documentation. So over the course of the tutorial, what we do is we take some data that is available through NOAA. It's sea surface temperature data, and it's originally stored in NetCDF format. And throughout the tutorial, by the end, what we end up with is that same data set, but it's been converted to Zarr. So if you've gotten what I'm going to do throughout the tutorial is keep the original tutorial on one side of my screen so that you can see what the source tutorial information, tutorial information is, and then on the other side of my screen, I'm going to put up the binder link that should come up for folks who have run the binder. Just checking in on the getter, it sounds like Ryan is kindly promoting some of the binder link, putting those back at the bottom of the screen, and installation instructions. Has anyone gotten those to work? Thumbs up in the chat if you have gotten that to go.
Rachel, I am seeing a note from one user in the chat that looks like the Pangeo Forge binder link. I'm sorry, the Pangeo, the Pangeo Forge binder link is perhaps doing better than my binder.
Okay.
I would say, Rachel, carry on with the tutorial, and I'll monitor the chat and help people get going. There are at least a few people who have the binder up and running and will be able to follow along.
Okay, sounds good. Okay, so that being said, then what we'll be doing is creating. So Pangeo Forge has a number of objects that it uses to create what's called a recipe. So a recipe is this definition, this thing that defines how we're going to transform our NetCDF into Zarr. So I like using the markdown cells to kind of give myself an outline. So our high level goal is to create a recipe. That's like the biggest thing that we're trying to do. In order to do that, we have a couple of sub-steps. So one of them is to create a file pattern. So part of the idea of the recipe object is that it's leaning on the fact that a lot of data stored online has a sort of a directory or a folder file type structure. So you can move through different folders in a directory and find a data set located in that. And it's leaning on the fact that those data sets are typically named in a predictable way. So that idea of predictably named data organized by file name is called a file pattern. So we'll want to create one of those. Within that, what we'll do is we'll create what's called a format function, which I'll explain in a bit. And then we're also going to create a concat dimension. So these are the things that we're going to be doing, and they're sort of nested here. I'll make this. That the format function, the concat dimension, is going to go into the file pattern, and the file pattern is going to go into the recipe. So there's all those steps that we're going towards in the end. So to create, so what we'll start with is creating a file pattern, and what we'll want to do is when we first start making a recipe in Pangeo Forge, the first step that you always want to do is get very familiar with the file structure of the data set that you're trying to convert. So in the case of OISST, which is the data set we're converting here, this is a diagram that shows what we have, which is a URL, noaa.gov/data/sea surface temperature, on and on. And then within that, there's folder for each month and month of each of the years that it's present. So we're noticing that our files have a single file, and each file represents one day. And the days of a particular month and year are then grouped together into a directory. So those are the big takeaways that we would get from exploring the file structure of the source data set. We would take that. What we want to do is take that then, a URL that represents our data set, and we want to make that into a template. So something that can be generalized to then pull out the URL of any data in our data set. So what I'm going to do first is copy and paste this string from the tutorial. which is, I forgot. So I'll actually take this URL, which is a single URL of a data format that you can see when I clicked it, it actually downloaded. I'm gonna put it into Python. And then what I'm gonna do is go through and replace any place where the URL changes. For example, here, where it changes by the year and the month. And I'm gonna put in curly brackets. So year, month, that's what goes there. And the other place where the URL changes is at the end, and that was shown as year, month, day. So this is a string that is a template that we could use to generate all of the files. So what we're going to do then with that is use that and take that to create the file pattern. So with our file pattern, I mentioned that we have two pieces of that. We have what's called a format function and what's called a concat dimension. So the format function is the thing that is going to take that this general template URL that we just made, and it's going to, given a day, it's going to give us back the actual URL for that date. The concat dimension is going to define how we want all those files to live with relation to each other. So we're going to tell Zarr that we want each of the days to sit on top of each other, stacked up in a big pile, and that information about how we want the files to stack is the concat dimension, or the combined dimension. Well, yeah, the combined dimension, which in this case we're gonna use concat. So let's start by getting a list of all of the dates that we have data for. So one way that you can create your list of dates however you'd like in Python. One way that I find particularly useful is to use pandas. So I'm going to import pandas as PD, and then create a list of dates using the date range function. If you were to go back and look at the data set, you would see that we have data from 1981 through, we'll just go with sometime in February. This tutorial uses the February 1st. You could go to wherever there's data. And there's data every day. So that frequency equals D is telling us that piece there. So what comes back here then is this list-like thing that has a date for every day in our data set. So I'm going to assign this to a variable called dates. In order to take those dates and tell Pangeo Forge how we want them to get stacked together, we're going to use Pangeo Forge recipes dot patterns, and we're going to use this concat dim object. So the concat dim takes 3 arguments. We're going to tell it what dimension it's concatenating over. So in this case, it's time, because every day is the thing that's getting stacked together. We are also going to tell it the dates that we want it to stack. So in this case, that nice list of dates we've already made. And we're going to tell it how many items there are in every file. For us, since one file corresponds to a single day, we have 1 item per file. So we'll say concat time concat dim equals concat dim time. We're going to use our dates, and n items per file is 1. So this concat dim is a Pangeo Forge object. Okay, so that's one of we're halfway then to our file pattern in that step. The other half of the way to our file pattern is called the format function. So that's the thing that will take our date and it will give us back, interesting. Well,
don't worry about that. It's just a weird thing that happens sometimes with the Dask Lab extension. It doesn't mean anything.
Okay, it means nothing. Continue. All right, great. So what we're going to do is make this format function. So we're going to make that. That's just a function in Python. And so we will we're going to make a function in Python that's going to leverage the strf time aspect of Python to do the formatting for our dates. So we will define a function. We'll call it make URL, and it's going to take as an input one of our time arguments, so a single date. We're then going to we're going to want to use our format URL that we use, our template URL from earlier, which is the thing that we'll want to give back. We'll return from our function, I guess I could say. And we'll want to substitute these places where we defined year month and year month day. We'll want to substitute them with the formatted version of our date. So year month can be made in Python by taking our time and doing strf time %y %m. And our year month day can be done with strf time %y %m %d. It does look like it's hanging a little bit. Let's see if I can stop the pandas import and keep going.
Looks like your kernel may have disconnected. So you might want to refresh that notebook.
Yeah, that sounds good. Do you see?
Just hit
do you
refresh on your browser. Like just.
Thanks. Uh-oh.
Oh, all right, binder.
Yeah,
It's giving us problems again.
indeed. I can pull this up locally rather quickly.
Lesson learned today that binder is not super reliable these days for doing these types of tutorials.
Yeah. All right. Okay, backup plan to the backup plans. Let's see if we can get this. So here what I have, just to, I think for the, so to keep going with the tutorial to kind of get to the part where we'll get to see this kind of all go, I'm gonna walk through this then on my local computer. So I'm using, right now what I have pulled up is the notebook that actually is the one that gets made into the tutorial. And so let's just rerun quick to get back to where we were previously. So I'm rerunning now to create that list of dates. I'm rerunning to create our time concat dim. I am running to make our format function. So this is where we just were with make URL. And what we see when we have make URL is that if we put in here, remember what our dates list looked like, is this long list of dates. And if we pick any one of them, the fourth one, for example, we can stick that into our make URL function. What we get back is the URL of that particular file. So this is a lot of, there's sort of a bunch of little steps that build up to making the individual pieces, but we're now at the place where we can make a file pattern. And in order to make a file pattern, what we're doing is giving it our function, and we're also giving it our time concat dimension. So to remember what those were, that make URL was that function, and time concat dim was this concat dimension object. And what we get back from that is a file pattern. So we can see what's happened is that there are 14,764 individual days in that data set, and that those are all going to get stacked over time. Each one is changes by time, and that will go together to make our recipe. So if we want to interact with this a bit more, to kind of, I guess, give it a little more, kind of maybe understand a bit more what is in there, we can iterate through it. And what's in it is an index and a URL in the pattern. And if we print them out, you can see what's inside the file pattern. And let me also do copy this little bit of code here, which is going to not print all 14,000 files. So just to look at this, we're seeing that we have this thing that's an index, and we're seeing that we have our URL. So the index is defining the relationship between files, and the URL is telling Pangeo Forge where to go and get that file. Okay, so relationship between files and where to go get the file. And that's what's inside of that file pattern. So in the end, it's fairly concise. So that's all of the first part of that tutorial, is creating the file pattern object. That's our first really big step. I'll pause for a sec. If any questions come up in the chat that we want to address before moving to the second part. Looks pretty good. So I'll pause for another couple seconds in case folks want to add questions, and if not, I'll keep going to the second part. Okay, so in part 2, what we're doing, this is part 2 of the 3 parts of the tutorial, and what we're doing here is that we're going to take our recipe or our file pattern and we're going to make it into a recipe. And once it's a recipe, what we can do is actually start creating the Zarr. So up here, what I just ran was a big cell that had everything that we wrote in the first part of the tutorial. Now that we've made our recipe object, or our file pattern object, creating a recipe is actually fairly quick. So we're going to import from Pangeo Forge recipes this xarray Zarr recipe, and then using that that class, we are going to give it the pattern, and we're going to tell it how many inputs we want to go into a single chunk. So we've been talking about chunks all morning, and we're going to tell it we want 10 files to go into an individual chunk. That number was chosen because we're kind of targeting about 100 megabytes per chunk is usually a good starting place or good size. So we are picking 10 based on the file size of the original objects. So we have back as this recipe thing, and it's got a lot of parameters you can look through, but really what this is now it's the definition of how to convert our data. So let's go ahead and actually do that. Before we convert data, actually run the recipe. It's nice to set up logging, which prints out some outputs, which are good for debugging and understanding what's going on. And in this case, because we're testing a recipe, we don't necessarily want to convert all 14,000 files of data right now. So we just want to do a small subset. So Pangeo Forge has a recipe, function for that, or a method called copy pruned. And what that does is it takes just a subset of the data. So we can see, looking at the recipe output, that now we have only 2 time steps in here. If we were to look at the original recipe, we would have that 14,000 time steps, but in our pruned version, we have just 2. So we're going to run our pruned version to just do 2 files instead of doing 14,000, which likely wouldn't work on my computer. And we can see that also in the file pattern would be another way to check that out. So in order to run this, we're going to do this thing where we convert our recipe to a function. This might be a little odd if you haven't seen this before, where you are actually having the output of a function is another function. But when we take recipe pruned and run to function, we're getting back something that is a Python function. So we run that like any other Python function, which is with the parentheses. So as we do that, we're seeing in the output that the various files are being cached and downloaded. They're opening them up in xarray. They're creating the chunks, consolidating the metadata, and converting to Zarr. So I tell you it's run, but if we want to check for ourselves and really see it, we can import xarray, as we were doing earlier, as a great way to read Zarr data. So we'll use xarray's open Zarr. We will take the target mapper of our recipe, which tells us where that this file was stored to, and we will open up our data set to see that we have some data in here. So it has lat long, it has 2 time steps, which is the amount that we tested. And if we plot it, we can see our sea surface temperature here in the end. So we've now gotten to the point where we have our Zarr version of OASST, which in our Python script, in basically these number of lines, a couple of lines, we've converted from NetCDF to Zarr. So that is, I think, where I'm going to pause and check for kind of questions, and we'll talk about that. What we'll do is we'll have a bit of questions, and then Charles will talk about the cloud side of. One of the things to highlight here, I think, is we have kind of 2 parts. We have Pangeo Forge recipes and Pangeo Forge cloud, which are sort of independent units. So I've been running this tutorials with Pangeo Forge recipes, which you could use and run completely on your computer and not do anything necessarily related to the cloud. But as we've been talking about, there's a lot of benefits of using the cloud and to really take that Zarr and kind of make the most of it. Running and hosting the data on the cloud is a great benefit of the Zarr, or is kind of most optimizes, I guess, the Pangeo Forge recipes tool. So the 2 independent pieces, but also very highly related.
Yeah, good. Thanks for pointing that out, Rachel. I think that it's really important to clarify that. Just to like zoom out and say a few words about what we just did, because we really kind of raced through this this detailed technical example. really what this Pangeo Forge recipes library does is it gives us a very concise and hopefully easy to use syntax to represent a rather large data transformation pipeline where we're taking nearly 10,000 NetCDF files and combining them into a single Zarr store. And it allows us to encapsulate that entire workflow in, about 10 lines of code. So, just kind of zooming up and explaining again why we created that library is to make it easier to do that type of workflow. Without Pangeo Forge recipes, you may be writing, hundreds of lines of code to do this type of conversion and transformation. So I think now, Charles is going to talk a little bit about how you can. We're trying to make it easy also to run those in the cloud.
Yeah, thanks for that's a helpful context, Rachel and Ryan. And I will open up another sharing window, and we'll look at how you would submit these recipes on the cloud. And I guess I'm feeling a little embarrassed that I now, even though I just shared my screen, oh, okay, maybe because I wasn't a presenter. Okay, great, show my screen. I was a little confused. Okay, so here we are. So I'm just going to actually talk you through this process as you would experience it as a user with the user-facing documentation. So before we looked at some slides just to summarize this, but this is all the user-facing documentation at Pangeo Forge -forge.readthedocs.io. Just as a recap, the introduction tutorial that Rachel just talked us through is, as you probably have already found, all located here under Introduction Tutorial. See if I can zoom in on this a bit more under Introduction Tutorial. All of the components of Pangeo Forge recipes that Rachel just presented to us are discussed in greater depth under the Pangeo Forge recipes tab of the documentation here, and there's in-depth discussion of a lot of everything that she just discussed there, including more in-depth tutorials for specific use cases. But what I want to talk about right now is the Pangeo Forge cloud. So I'll just talk you through some of these concepts, and then we'll look in a moment at GitHub where you would submit your recipes to be run on the cloud. So just recapping from our intro slides, a few core concepts. Catalog shouldn't be any mystery what that might be. That's our catalog of data sets, which is certainly in an evolving state as this has just been launched within the last number of weeks, essentially. But data that's built on Pangeo Forge Cloud will be reflected in the catalog. And sort of a trend I want to highlight here is that for each of these core concepts, we have the Pangeo Forge documentation page here, but also our Pangeo Forge website sort of dashboard representation. So this is just pangeoforge.org, and we have a dashboard here that keeps track of kind of the state of the system. So I'll be talking about each of these concepts in the documentation, and there's also a link here that will bring you to the dashboard representation of those things. So as we talked about before, feedstock is as it is in Conda Forge, a feedstock is a GitHub repository that houses, that's the container for recipes. A recipe run is an individual execution of a given recipe within a feedstock. For these, it might be easy to page over and look at what a recipe run looks like. So if we looked at a feedstock, for example, this was a demonstration feedstock. I'm not sure, maybe it doesn't have any recipe runs on it. Let's look at one of these other feedstocks. So on this feedstock, for example, we have a number of different recipe runs. And for a given recipe run, when we click through, I think we will actually see some logs. These are the logs, the execution logs for that given run. So the actual run itself is tracked here. I'm making a mental note, which I think we have already here, that we should be listing the output destination of the data set there. And as we talked about before, a bakery is the cloud compute infrastructure that we use to execute recipes. There are, as shown by these repositories here, implementations available for all 3 major cloud providers to establish bakeries for Pangeo Forge. Currently, if you look at the dashboard, we have just a single bakery, which is called Pangeo Lamont-Doherty Earth Observatory, LDEO NSF Earth Cube. So this is our Lamont-Doherty Earth Observatory NSF funded bakery. So these are just some core concepts, but the important concept thing to think about here is how would I like to kind of participate in Pangeo Forge, and that's discussed in the recipe contribution section of the documentation. The first thing to note is that there is a great way to participate in Pangeo Forge with writing no code at all, and that's to just open a new issue on this issue tracker of the staged recipes repository. So this is also something we've borrowed from Conda Forge. Those of you that have used Conda Forge as contributors, recipe contributors, may know this. We have a repository within the Pangeo Forge organization called Staged Recipes. And this is essentially the entry point for all contributions to Pangeo Forge Cloud. A very great way to participate in Pangeo Forge as someone who's familiar with a particular data set that you'd like to see in cloud optimized form is to just open an issue and add the proposed recipe tag, and our label rather, and you can see there's quite a number of these here. If we click on any one of them, what we see is a description of the data set, where it's located, some thoughts about how it might be transformed. Here we see Ryan chiming in with some suggestions. There's a number of these, obviously, and you could take your time after this presentation to look through them. But this is a great place to start ideating, to start brainstorming with others about how you would design a recipe for a particular data set, and without having to write any code. So this is a great entry point. When you're ready, perhaps you've already done that, or perhaps you want to jump into just writing your own recipe. Essentially, there are 2 required files to contribute a recipe to Pangeo Forge Cloud. The first is the recipe module, and that's the Python file that contains the components that Rachel just described to us. There's a lot of links in here that in the documentation that can point you back to the recipe docs to figure out how you might write your recipe module. And again, an issue is a great place to discuss ideas about that. The next one is a YAML configuration file called meta.yaml. And the meta.yaml configuration file, we have links here as to what that looks like, and I'll show you an example in a moment, essentially defines the configuration for your recipe, what bakery it will be run on, which for now will always be the Pangeo Forge NSF, the Pangeo-LDEO-NSF Earth Cube bakery that we looked at a moment ago. What bakery will be run on, the license of the original data, your name, your GitHub username, your ORCID ID if you have one, etc. So these are sort of just configuration, a configuration for your recipe. And once you have those 2 files, or a draft of those 2 files, that's a recipe module and a meta.yaml, you will make a pull request to Staged Recipes. There's a few sequential steps here for making a pull request, which are maybe familiar to anyone who's done that before. But if we take a look at some pull requests here, just take a look at the first one. We can see that this contributor has added the meta.yaml. So this is, kind of an example of what a meta.yaml looks like when it's contributed as a PR. We have a title for the recipe, a description, a listing of what version of Pangeo Forge was used to write the recipe, some information about the data provider, and the contributor and the bakery again that should be used to run the recipe. And then here is the recipe file itself for an actual recipe for a real data set out in the world. Well, the one that Rachel just showed was also a real data set, but for some data sets are a bit messier to handle. So this one is a few more lines than the one that Rachel demonstrated for us, but still only less than 50 lines. And we have some white space in here too. So this is what that pull request would look like. You have 2 files contributed. And as described in the documentation, when you've submitted a pull request, there's a series of pull request checks that will be performed. So if we go back to the conversation, you'll see a series of comments by our helpful Pangeo Forge bot, which is this little smiley anvil character. And the Pangeo Forge bot is essentially just watching the staged recipes repository for any pull requests that come in and making assessments of their formatting and their structure, and if they meet the expected criteria, the Pangeo Forge bot will make essentially a test recipe run for your data set so we can start into the testing process. So if you're interested, it's a bit beyond the scope of the few minutes we have left to go into all of those checks, but we have a reference page. It's linked here, and I'll show you also in the navigation tree or the table of contents. There's also the reference page here. So this reference page in the documentation talks in exhaustive detail, step-by-step detail, but very clear. You can look through everything if you're curious that the Pangeo Forge bot will be examining about your recipe. But if you're not interested in that, all you have to do is just open a PR and the Pangeo Forge bot will tell you what you have to do next. So in this case, actually, there weren't any points of feedback for a kind of on a structural level. I think this one, for example, if we looked at this, we'll see that, for example, right here. So the Pangeo Forge bot chimed in immediately and said, I don't see a meta.yaml in this pull request. I only see these files. In this case, it says, sorry, I only want to look for the .yaml extension, not the .yml. So in this case, we had a .yml extension for the meta.yaml, and the Pangeo Forge bot just said, this is what I see. And then the contributor made a correction there, updated the file name. The Pangeo Forge bot found another issue, which is that there was a missing field in the meta.yaml, and eventually we moved on from there. So I'll wrap up the PR discussion section here with just the thought that you don't need to know what the Pangeo Forge bot is going to do before opening a pull request. If you're curious, you can review the documentation here, but the Pangeo Forge bot should tell you what is needed. And if it doesn't, one of us will chime in and correct it. So I'll just wrap up, and we're about 12 minutes to the hour now. And so I'll just wrap up with another 2 or 3 minutes discussing what happens after the pull request. And then we'll have time for some more questions. And of course, you can put those in Gitter now if you've already thought of them. So what happens, how do we get from a pull request to a feedstock? Again, this is discussed in the documentation. After making a pull request and the pull request checks being performed, we go to creating a new feedstock. So to create a new feedstock, one of the maintainers, it might be one of the people presenting today or someone else, will have made an assessment in addition to the feedback of the Pangeo Forge bot that the pull request is ready to merge. Here's an example of a pull request Rachel made. We had a long discussion, you can see here. Once the Pangeo Forge bot ran a test of the recipe in the prune form, like you saw Rachel do in the tutorial, and reported back with representation of the X-array data set of that pruned recipe. And we discussed whether or not we thought that was what is how we expected to look. And ultimately, we merged this pull request. So once that pull request was merged, it's automatically created into a new feedstock repository. So you can see that pull request became automatically this repository. And this repository was given a feedstock directory in which the recipe was deposited. Here's the recipe. This recipe is 42 lines. And the meta.yaml configuration was also put in this repository. And from here, the production deployment of the feedstock begins. In this particular case, we're actually debugging that this week. So this deployment has actually failed. But this feedstock can be deployed, and that will bring you to one of these recipe run pages that we looked before. And this is essentially tracking the logs of the full recipe deployment. When one of these succeeds, it would be added to the catalog, which right now is just a very simple plain text list of URLs, and very shortly will be a much more engaging user interface. The last thing I'll say is that, just as I had said in my initial slides, these feedstocks provide a place to discuss the quality of the pipeline, discuss the quality of the recipe, and a venue for improving that collaboratively over time. So it's a very transparent process. And as you can see here, I mentioned we're debugging this deployment. Here is just such an issue discussion. I had posted this here. We're discussing why did this deployment fail, and this is a very long thread, but this is on public GitHub, so you're welcome to chime in if you have thoughts on this today or soon. So that brings us, when we refer back to the documentation, to the end of the contribution cycle, which is maintaining the feedstock. This feedstock can be run once, but perhaps if you have data that has evolved or updated, you can make pull requests to these feedstocks and then rerun deployments of them in response to pull requests to these feedstocks. And hopefully then when you or your colleagues or other members of the community create publications based on these data, you can link back to these feedstocks in that publication and say, and this is the reproducible pipeline that we used to move the data from, let's say in this case, a NOAA server from a known archival endpoint of a particular data set into the cloud optimized format for the data, for the paper, which is a step in the process that's often obscured. So I will pause there. We're a few minutes before the hour, and Rachel and Ryan may have other things they want to share, and we're open to questions at this point.
So we had one question in the chat, either Ryan or Charles, if you want to jump at that one. It's about, is there a way to deal with data sets that aren't directly accessible in archived NetCDFs, but are instead by data request through an API?
Right. I'm
Right
reading that
now,
question.
that's not capable supported, but very soon it will be. Right now, we can basically open any data set that Xarray can open through a URL. So that could be an OpenDAP link, a GRIB file, a NetCDF file. But if it is something that needs some special processing to massage into that format, a custom opening hook is required, and that's under development right now. Maybe another thing worth mentioning is yesterday there was a lot of discussion of Kerchunk, which is a tool that makes it possible to access, these binary file formats like NetCDF or HDF or GRIB using Zarr semantics without actually converting the data to Zarr. But it requires building up an index of all those files. So Pangeo Forge recipes includes workflows that allow you to build up these indexes using Kerchunk to then build one big virtual Zarr data set out of your NetCDF files without actually having to copy the NetCDF data to a new format, which I think is something people are very interested in.
Yeah, I've just highlighted, that's a great point, Ryan, and I've just brought up on screen again the location in the docs where you can read a notebook tutorial about how to do that. Our recipe class for Kerchunk is actually called the HDF reference recipe, but that uses Kerchunk for the actual implementation. This shows you how to go through the steps starting from the file pattern, which Rachel introduced, and beyond to use that recipe class. And there's also a more detailed description of that in the API documentation, if I can navigate to it. Right, the HDF reference recipe is described in more detail here.
So Leaf is asking, we have quite a large intake catalog for a field campaign which uses NetCDF files, but none of them in Zarr. It would be really nice to be able to convert everything in the entire catalog to Zarr. Is there something like that which would traverse an entire intake catalog to create a Zarr back mirror? That's a great idea, Leaf. It would be very easy to implement here. But it doesn't work today, but we would love to support that. Another one is from a threads server. Like if there's a catalog exposed by a threads catalog, it would be nice to be able to walk that, or a stack catalog for that matter. That's actually much easier than what Rachel showed today of manually putting together this file pattern. If there's a catalog and you want to operate on a specific sort of branch of a tree of a catalog, it should be very straightforward to automatically generate the file pattern inputs from that. So great suggestion.
Just to clarify that, Ryan, I think what you're suggesting is that the intake catalog could be used just in the existing Pangeo Forge recipes within a file pattern to extract the URLs?
Either that or have a specific, or we broaden the idea of the inputs such that you can essentially take an intake catalog and that will automatically generate the inputs without having, you could do this, you could code this today inside a file pattern function, but I think there's a more direct path.
Right, that makes sense.
All right. Thank you, Charles. Thank you, Rachel. And obviously, thank you, Ryan, for delivering the tutorial.